Video, we're going to be describing some polynomial functions and some behavior that happens in their graphs, and we can actually check that behavior by doing a few algebraic methods here. First of all, we're going to use what's called the leading coefficient test. This will describe what is going on the farthest ends of our graph. So not telling us a whole lot about what's going on in between, just what's happening at the farthest ends of our graph. That's called end behavior. There are really only two cases, and inside those two cases we have two more cases, so four possible outcomes for all polynomial function end behaviors. What we're going to be looking at is we're going to be looking at the leading term, we're going to be looking at the coefficient, describing whether it's positive or negative, and we're going to be looking at the exponent and describing whether it's an even or odd number. That's all we have to do. If your leading exponent is odd, well then you will get one of two end behavior patterns. If that leading coefficient is positive, well then the ends will look just like a linear function with a positive slope going up from left to right or increasing. If your leading coefficient, that number in front, is a negative value, then it's going to act just like a decreasing linear function, meaning it's going down from left to right. We don't know what's going on in between at the moment, but we do know that on the very ends or extremes of our graph there, it's going to act just like a linear function. So that makes it pretty easy if you know about your linear functions. Second thing that could happen is what if our leading term's exponent is an even number, like it is down here. In that case, it's going to act just like a quadratic or a parabolic behavior, I guess, on the ends here. So it could act just like a positive quadratic or something that is concave up or opening upward, at least on the ends. We don't know about the in-betweens, but on the ends, both arms are going to be pointed up. If your leading coefficient is negative, well, it's going to act just like a negative quadratic, meaning that the arms of the parabola are going to be pointed down. Again, we don't know what's happening in between, but on the ends, we're pointed downward. So we only have two behaviors. Either it acts like a linear function on the ends, or it acts like a quadratic function on the ends. Pretty easy. Let's practice looking at some functions and see if we can come up with their end behavior. In this first example, we see our leading term here has a negative coefficient and an odd exponent. So an odd exponent is going to act like our linear functions. A negative coefficient is going to be acting like a decreasing linear function, so going down from left to right. Right here we'll see some notation that looks a little weird at first. You'll actually see similar notation if you know anything about limits, or if you're going to see limits in the future, you'll see similar notation here. This arrow right here we read as approaching. So we read the statement as x approaches negative infinity, or as x moves left on the x-axis, going more and more negative. Our outputs are approaching what? Well, if it's this behavior, your outputs are going up as you move left on the x-axis, up towards positive infinity. Second part of it, as our x values approach positive infinity, or in other words, move right on the x-axis, plugging in more and more positive values, our output is going to approach, well here we can see if we move right on the x-axis, our outputs are going down or approaching negative infinity. So being able to sketch out that end behavior allows you to figure out what your outputs might be doing as you move to the ends of your graph. Next one, we see a polynomial with a leading term here, an exponent that is even, and an invisible coefficient here, but it's positive 1. So we have a positive coefficient and an even exponent. Well, we know that we're going to be acting like a positive quadratic, where our outputs are both moving up. So as x approaches negative infinity, or as we move left on the x-axis, our outputs are going up towards positive infinity, which is also the same as if we go the other direction on our x-axis. As x approaches positive infinity, our outputs are also going up the exact same amount. So both positive infinity answers there. Hopefully you can see that if our exponent is even, our end behavior signs are going to be the same. They're either both going to approach negative infinity or both approach positive infinity, whereas if our exponent was negative, our outputs are approaching opposite things, either both one positive and one negative, or vice versa, one negative and the other positive. So use that to your advantage to come up with and think about the end behaviors of your graph without having to graph it in your calculator. Another thing that we can do algebraically is we can think about what our zeros are, also called x-intercepts or roots or solutions to an equation. If each of our terms have a common factor that we can factor out, well, we can try factoring and then see if we can set up our factor pairs equal to 0 and then state what would make it 0. Also, what's unique about polynomials is that their leading degree is the number of possible real zeros. So because our leading exponent is 3, we know we have at most 3 possible real zeros. It's not that we have to have 3 real, but we can have at most 3. We could have less, but we can't have more. Also, if you subtract 1 from that leading degree, that will be the possible number of relative extrema points. So the number of relative maximums or minimums. That's the number of possible ones, not that it has to have it, but they are possible. So let's take a look at this polynomial and see if everything pans out here. We should have at most 3 possible real zeros and 2 possible relative extrema points. Because each of our terms have an x in common, we could factor an x out. But that leaves behind a quadratic. And so since we know how to factor our quadratics, we could use that pattern. Factor it into 2 binomials, factors of -2 that add up to -1. That would be the values -2 and +1. If we set our factor pairs equal to 0, then we can describe the values at which those x-intercepts occur. So the first spot just is an x. So think, what value could you plug in here to make the whole thing 0? Well, we know if that equals 0, everything multiplied to that would be 0. So that value right there for our x-intercept is 0. A little strange to say the 0 is 0, but that's what we say. Also, if you set x minus 2 equal to 0 and solve it algebraically, you discover that +2 is another x-intercept value. You could also think what's the opposite here that would make it 0, so that when you multiply, everything is 0. +2 would be 2 minus 2, which is 0, turning the whole thing into 0. Same thing over here. Plugging a -1 into that spot would make the whole thing 0. Or you could set that equal right here, subtract 1, and figure out that it is -1. So we came up with our 3 real zeros. We'll graph it, and then we could also look at the fact that it does have 2 possible relative extrema. It's got 1 relative max and 1 relative min. One other thing that I want to talk about while we're there is if we look down here, there's some more definitions that we need to talk about. In your factor pairs, as they look right up here, that's what this is saying. If an exponent above your factor pair is more than 1, we're going to have what's called multiplicity of zeros. In this case, all of our exponents above our factors are 1, and so we don't have any crazy multiplicity happening here. So if our multiplicity is 1, graphically what's going to happen is that at each of those x-intercept values, the graph is going to cross the x-axis at those spots. So at x equals -1, you should see the graph crossing. At x equals 0, the graph is going to cross back again. And then one more time at x equals 2, the graph is going to cross the x-axis one more time. So if your multiplicity of your zeros is 1, when you look at the graph, you will see the graph crossing the x-axis at those points. Slightly different than what's going to happen in our next example, which we'll talk about. Once again, we could look at our polynomial, discover that our leading degree is 4, so we're going to have at most 4 possible real zeros. If we subtract 1, we're going to know that we could have at least 3, or at most, 3 possible relative extrema points. And then because our two terms in this polynomial have some common factors, we can factor to solve. Let's factor out a -2 and an x squared. So factoring out -2x squared leaves behind x squared minus 1. You could distribute that back in and make sure that you factored correctly. You should get back to the beginning. Here we have our factor pairs. If we set each equal to 0, we could solve it algebraically or simply think about the opposite of what's going on. If we plug something into this first one, what would make everything 0? Well, if we plug a 0 in, we get 0. But as we see, above that factor pair, we actually have an exponent that's more than 1. And so because that 0 value is our x-intercept, but raised to the power of 2, we say that that is a multiplicity of 2. And graphically, you're going to see that rather than crossing the x-axis at 0, the graph is just going to touch the x-axis and then go the other direction. So it's not fully going to cross over. So that's the difference graphically when you have zeros that have different multiplicities. They're either going to cross the x-axis if your multiplicity is 1, and if it's anything bigger than 1, it's just going to touch at that x-intercept. Now graphically, you can't really see the 0 happening more than once. You'll just see the graph touch at 0 and then go away. So really the only way that you can know that is in either knowing the definition, knowing that when it just touches and moves away, that's a different multiplicity. But also more specifically, you would only know it in its algebraic factored form. Knowing that the exponent is 2 means our multiplicity is 2. If that was a 3, our multiplicity would be 3. And so you, again, wouldn't know that by looking at the graph. You'd have to go back to look at it algebraically here. For our other factor pair, we have x squared minus 1. That's just being raised to the first power, so that's just a multiplicity of 1, whatever those zeros are. There's actually 2 zeros in here because we got a quadratic. Think that we got to add 1 to both sides and square root both sides to solve for 0 there. And whenever we square root a quadratic equation to solve it, we always get 2 possible solutions, a positive and a negative solution. So we have our zeros occurring at -1 and at 1, each with a multiplicity of 1, meaning that the graph is going to cross the x-axis at those points. And then our third and fourth 0 is occurring at 0, and because that's a multiplicity of 2, our graph is just touching the x-axis. So a lot going on there with our zeros and the graphs as they behave around them. One last thing, actually 2 last things. What if we have a polynomial that is either so big or just really hard to factor that we don't want to bother factoring? Well, one thing we can do to find our zeros is use what's called the intermediate value theorem. And so if you're looking at your data table, what you can do is you can actually see on your data table where you have a mixture of negative and positive outputs, meaning that if we went from negative to positive on the y-axis, we must have crossed 0, or vice versa. So the intermediate value theorem is just kind of a quick and easy theorem that you can use to determine whether or not we have zeros occurring between 2 numbers. And again, if you're just looking at 2 inputs and you look at their outputs and it's in between a negative and a positive, then you must have a 0. It must be crossing the x-axis somewhere between those 2 numbers. So really the only thing we can do at this point is just look at the graph. We can determine some things. We know that there's at most 5 possible zeros. We could look on the graph and then we could see that actually we only see 3 zeros on our graph. And if you were able to factor this, and I kind of cheated, I just looked at our textbook for this one, you would see a factored form that could give you your zeros algebraically, but notice that really only part of it is solvable, whereas the other part of it here gives us some imaginary solutions. And so we'll get our 3 real zeros that we can see on our graph from this, but then there are 2 more imaginary zeros that we can't even see on our graph happening. And so there's our 5 total zeros. But again, graphically, we can't really see that. We can only do that algebraically, maybe. And to factor this into this is actually pretty complicated. I wouldn't worry too much about it at this level of math, although if you're in college, we'll definitely maybe talk about some theorems or some rules that would help you factor that. All right, lastly, what if we work backwards? What if we know what our zeros are, or they're given to us? Then what we could do is we could work backwards and write our factor pairs, or the number of factors, however many zeros there are. And then from there, we could graph it. We could expand it if we wanted to. No reason to, though. So knowing that we have zeros at, or x-intercepts at -1/2, 3, and 3, well, here we see that multiplicity of 2 happening. So we know in our factor pair, we're going to give it an exponent of 2. If your 0 is 3, or your x-intercept is 3, you know that comes from the factored pair x minus 3. What would make that 0? 3. And because there's 2 of them, our multiplicity is 2, we'll put that exponent up there. Not the only way we could come up with 3 as a 0. We could get fancier. What if we said 2x minus 6? That would also give us a 0 of 3, or an x-intercept of 3. And so if you can imagine, we could play that game for quite a while and come up with lots of different ways that we could come up with a x-intercept of 3. So there's many solutions whenever doing this, not just one. One more time, let's try and come up with a 0 factor pair for x equals -1/2. Well, if that's x plus 1/2, that would be the most basic way to do it. But you could also get fancier and do something like 2x plus 1. That would give us the exact same x-intercept value. Or 6x plus 3. Lots of different ways to do it. There is not just one solution or one way to write the equation. However, each of these equations would give us the exact same graph with the exact same zeros. So just something we can use, especially next time in class. We'll be looking at zeros and working backwards to try and divide polynomials. All right, so once again in this video, we talked about how we can look at behavior of polynomial functions using a lot of algebraic methods, but don't ever forget that you can just look at the graph and verify all of these little methods. Make sure that you're doing it correctly.